Hello there, welcome back to our channel, and on your screen you see we are going to understand the concept of class A amplifier, and we see where this amplifier is used and how this is used. So you actually can see that from our previous model. This is a classic example of BJT biased as a small signal amplifier, and this can also be called as a class A amplifier. And basically we have seen the working principle of it. You have an input signal, you have an output signal, you apply a small signal AC and you get an amplified version at the output. You have resistor R1 and R2 that are used for biasing the resistors, biasing the transistor actually. Then you have a emitter degeneration resistance to make sure that your circuit is insensitive to the changes into the operating point due to temperature, distortion, noise, etc. So it's kind of provides negative feedback into the circuit. And there is this bypass capacitance. C in and C out are your output capacitances and input capacitances. They are also called as coupling capacitances. RC is the load where you deliver uh, your collector current flows. And here from the output, you actually connect a load to which you deliver an output current. Now, when we talk about class A amplifiers, we usually talk about using them for audio amplification, or more popularly known as class A audio power amplifiers, right? So we call it as a class A because your output current to your transistor conducts current for full 360-degree of the cycle of the input waveform. That's why we call it as a class A amplifier. Okay, and now the same circuit can be also used as power amplifier. So when you talk about using it as a power amplifier, we say we want to use this as a large signal amplifier. So here there is a definition of, so you want to use it as a small signal amplifier, that is fine. You want to use it as a large signal amplifier, it is also possible. So when you talk about small signal amplifier, you have input and you have amplified output inverted though. Your output power, your power, which is the product of voltage into the current, is in the range of microwatts, okay, or less than, let's say, 1 milliwatt. So that's the definition of using this circuit as a small signal amplifier. But as a large signal amplifier or a power amplifier, your power delivered to the load is in the range of milliwatt. Your power is in the range of milliwatts, or even few milliwatts, even more than 10 milliwatts. Okay, so the example of using it as a power amplifier in audio amplification, for example, you are delivering the output current to the load, which is a loudspeaker, which has a, let's say, an resistance R equal to 8 ohm, for example. Okay, so in that case, or you want to drive the motor through the load current, and then in that case you can use it as a large signal amplifier. So the idea is to deliver your large load current. Then only you call it as a power amplifier or large signal amplifier, and then the job is done. Such job is done by the transistor is called as output transistor or power transistor. And in that case, you want to use it as a power amplifier, then you have to use a power transistor as output transistor, such as 2N3055. You cannot use it, for example, BC547 or 2N2222. These two are the small signal transistors. So you want to use it as a small signal amplifier, this circuit, then go for BC547 or BC107 or 2N, double two, double two. These are called as small signal transistor. When you talk about the power transistor, it means its voltage and the current ratings are high. Okay. Now the third concepts of using the power amplifier or large signal amplifier is the efficiency. Efficiency means you have an audio signal and then you have a large power output signal that you get. So it's like your AC power in and then you have a AC power output delivered to the load. So how much is the power is delivered to the load divided by how much is the DC power or quiescent power dissipated into the circuit while doing that action. So this factor is known as efficiency expressed in percentage. So it is the ratio of power delivered to the load divided by how much power is dissipated during the delivery of that load multiplied by 100. So for example, if your circuit dissipates 1 milliwatt of power and the output power that you get is about zero point 0.3 zero point 0.3 milliwatt. Okay, so 1 milliwatt is the dissipated power while delivering zero point 0.3 milliwatt at the output. In that case, your efficiency would be zero point 0.3 divided by 1 multiplied by 100. So it will be 30% will be the efficiency. Okay, so idea amplifiers efficiency is that the idea here is to deliver the maximum power, which is an AC power to the load, while DC power in the circuit has to be kept as low as possible. You have to improve and enhance the power delivered to the load, and you have to reduce the power dissipation into the circuit. Now, the Class A amplifier, using this circuit as a Class A power amplifier or large signal amplifier, has a drawback in terms of efficiency. So usually the efficiency of such circuit is less than 30%. Second drawback is that your output transistor here is passing the same load current even when there is no input signal applied. So when you switch on the DC voltage, your transistor is on and it is delivering a large current to the load. So it means even if you have no signal, the transistor is on. That means you have a large current that transistor has to handle. So to to handle such situation, transistor is mounted on a large heat sinks, and therefore we say that the large heat sinks are needed for the output transistor. Now, there is a one question: how to increase the power gain and remove the need of heat sinks? So there are 2 points. One, we want to improve the efficiency of the amplifier. Currently, we are limited by less than 30% efficiency. And second issue is we need a heat sink because the transistor is always on. So to solve this problem, you have a solution. And solution is that you need to use heatsink. And the solution to improve the power efficiency is to use the special transistor called as Darlington pair. So Darlington pair is composed of two transistors, let's say Q1 and the QT. And the arrangement of this transistor is that the collectors of the two transistors are shorted. The emitter of the first transistor is connected to the base of the second transistor, and the emitter of the second transistor is separate, and the base of the first transistor is also separate. So this configuration is called as Darlington pair. So what is the advantage of using Darlington pair instead of a single transistor as we saw in the previous circuit? So the advantage is that since you are using the two transistor, they have individual current gain, that is beta 1 and beta 2. Remember, beta is DC current gain of the transistor. Okay, it is also called as HFE. So instead of one transistor, since you are using two transistor, the collective beta is beta 1 times beta 2. So that's why you say the Darlington pair has a very high current gain. So now the transistor is capable of handling a very large current through it. Second advantage is that it has a high input impedance and it has a low output impedance. Okay, so because of that, you have a reduced power loss into the circuit, and therefore you have a reduced heat into the device. So you got the current handling capacity of the transistor up, and you got the heat dissipation into the circuit or into the transistor down. So that's why this is the advantage. So we solved the first problem of current handling and the heat sink. How about efficiency going from less than 30% to more than 30%? So the idea is use such arrangement called as transformer coupled class A amplifier design. So you have the same circuit, let's say VCC, you can use the biasing through the resistor RB, or you can also use the same biasing as in the previous circuit, such as voltage division biasing. And then instead of load resistance, you use a transformer where you have primary winding, you have secondary winding. This is the ratio of turns into the primary winding into the turns into the secondary winding. The voltage V1 is the voltage across the primary winding. Voltage V2 is the voltage across the secondary winding, which is also the voltage across the load, and therefore it is the output voltage. Now, using such transformer coupled circuit, the efficiency, the power conversion efficiency of the amplifier is improved because the transformer helps to match the impedance of the load to that of the impedance of the amplifier. So, um, so the efficiency in this case can be improved up to 40% or even large. Now, we achieve the improvement in the efficiency also, but there is a drawback. First drawback is you have to use the bulky transformer, so size is an issue, and therefore cost also is an issue. Using the expensive transformer and the heavyweight transformer in building a class A amplifier is always problematic. Second thing is that the transformer may experience a back EMF problem. Therefore, that back EMF or reverse voltage can raise the possibility of damaging your transistor and therefore damaging the circuit. That's why you have to consider whether to use Class A amplifier as a transformer coupled or not. So we have seen Class A amplifier with the classic load RC. Then we have seen the transformer. Then we have seen the Class A amplifier with the Darlington pair. And now we have seen the Class A amplifier with the transformer coupled. We have seen the pros and cons of each of the networks. So now if you are liking this video, you will click the like button, subscribe to our channel, share this video with others for wider reach, and if uh, you are interested, then stay tuned for more engaging content like this. Till then, wish you happy learning. Stay tuned.